get on the good train.
Yeah.
Okay, so I finished with my roll. Robbie, good?
Yep, I'm good. Well, just take notes, guys, at home, just like you were in the classroom. I mean, take your notes and then refer back to the videos and anything you got in your notes and on the videos on the quiz or the test.
Yeah, and you can tell by Professor Vermelin when he speaks about something that's probably a good time to write it down. When I emphasize something in the book and I stay on it a good bit, sometimes you'll even hear me say, wow, that sounds like a good test question. Well, guess what's going to happen?
Yep.
It's going to be a test question. So be in preparation for that. Mr. Christian Cox?
Yes, sir.
You were my man today, weren't you?
No, sir, I did it. Yes, the day before. For yesterday.
Who did I?
McAllister did it yesterday, right?
Cole Templeton.
Yes, sir.
Cole Templeton was my man today?
Yeah.
Okay, buddy. I'll tell you one thing. For some reason, it seems like you're doing a lot of them, but go ahead.
TM4. Can you look it up on yours and share it?
Absolutely. Stand by. I would assume YouTube, correct?
Yes, sir.
10-4. And what am I searching for?
It's called Lineman Universe Grounding. Oh crap. I think it's light pole. Hold on, let me double check.
Lyman Universe Grounding
Power Lines.
Power Lines. Sounds like an excellent subject.
Yep.
I see a guy that's standing here in a black t-shirt with a yellow cable in his hand. He's got a Lyman Universe t-shirt on.
Yeah, that's him. He's kind of just explaining the whole situation.
10-4. Let me bring it up and I'll get it in the share.
Appreciate it.
Somebody asked me, what are you doing here? What are you trying to say? Here's what we're trying to say. We're tired. We're taking a stand.
That was Lindsey Graham again. All right, share screen. Lindsey sure is pushing the.
Oh, yeah.
Okay. Yeah, everybody see my screen here?
Yes, sir.
10-4. Here we go.
What's up, guys? Welcome back to Lineman Universe. Today we're going to be talking about grounding. How to ground a line to work on it. De-energized. I know a lot of y'all are probably going on Hurricane Dorian, so what I did was I threw this together last minute just to give you a heads up for those of you who don't know, who haven't grounded a line or who've never been on a hurricane. Okay, guys, let's just start out by telling you what grounding is. When you ground a line, it's to work on it, de-energize. That's to make sure that no power, if somebody is to backfeed or energize it from a different direction, so you don't get any power coming back to you where you're working on that line. We're also going to show you some of the parts and some of the procedures to ground so you have a better idea. Now remember, if you're not qualified or you don't have somebody there that is qualified telling you what to do, don't do it, because you're probably going to die and you're probably going to kill everybody old enough to die. So there's that. Okay, first off, let's go ahead and slip our really cool Lineman Universe gloves on. First thing we're going to look at is a grounding chain. Now, what is a grounding chain? A grounding chain, basically, what it does, you clamp it on the conductor, right, to make sure that it's going to go from the phase all the way down to the neutral, or it's going to go to ground. So if it wants to become energized, it's going to hit this, travel down here, and take it to ground. You know, when your foreman says, hey, man, he's like, go up there and ground that line. And you're like, well, is it dead? You know, and they're like, what are you asking me for if it's dead? Of course it's dead. Well, how do we know? Okay, so what we have here is a voltage detector. This here is going to tell you if there's voltage in that line. Before you go sticking the ground on it and you get blinded by the light or get a really bad sunburn, this is going to tell you if it's hot. Now, when we hear that sound, it's searching, right? Okay, you actually have to touch this to the wire. So let's just touch it to my studio light. Okay, that's hot. Now that's set on 240. Let's jack it up to 15 kV. Guess what? It's not even recognizing it. So remember, have it within the range of what you're checking for, And we're not going to do this by hand. I think actually on here it says nothing over 220 volts by hand. You're always going to want to put this on shotgun. And we'll show you how to do that here in a minute. So that's your voltage indicator. When we put a grounding chain up, you don't just put one there at takeoff, you know, from your neutral to your primary. You got to have yourself boxed in. You have to have it at the takeoff, and you have to have it down there on the other end so that nobody juices it up coming from a different feed. You're going to be boxed in. So you're going to be working in the middle of both of those grounds. And a lot of places, they want you to have a visual. You'll have them at each end, and then you'll have them right there in your work area in that span that you're working on. So you follow your company safety procedure. Another thing is a flag. When you have these up there, if they're riding through, they're like, well, we're going to go ahead and heat this one up. I don't know why they do that, but stranger things have happened. And you don't have one of these flags up there, well, guess what? They can run through there and be shining, or they can run through there in the middle of the day and say, oh, yep, everything's good. Well, this here is going to help them to see that you've grounded that line. And I'm not sure what your company's policy is, but a lot of them you have to put your name and your phone number and information and who's got the clearance on that line. Fellas, do not ever take somebody else's grounding chains down, okay? It's just like, you don't do that. You get kicked off the storm, you probably get beat up by whoever's chains there was. So don't do that. That's not cool. Yeah, it's just something we don't do. Guys, this is a mechanical, okay? This is a temporary jumper. You can't use this for a grounding chain because this ain't the right tool for the job. Now we know what a grounding chain is, okay? And now we know what a grounding chain is supposed to do. So there's another thing that we need to learn if we're going to be grounded. And let me get it right here. It's super long in this little tiny studio. Guys, this is a shotgun. See that little hook right there? Okay, what that does is that little hook allows for you to put stuff in there, right? It's going to hang on to it. You could take and check the voltage off of your stick here. Wish I had more room. I gotta get a bigger studio if I keep doing this. This here is a hook, hang it off the phase or whatever. You can hang it off the wire, you know, while you're waiting. You see how it operates right there. So we got our shotgun here. See this little mechanism? This is how we make that hook come in and out. It travels up this little rail. You're like, okay, well, it's open. Guess what? It's not open. You got to push this and this little safety button right here to make it open. Now it's open, right? So now she's loaded. Don't ever send that up to a lineman without that hook being open. Okay, guys, when we're loading the grounding chain on there, you can take it, set it on there like this. You see how that's locked in right there? All right, guys. You see here? You see here, we loosened her up. That clamp is ready to be sent up to the lineman. This is for the grunts, or the ground apprentices, I guess you call them. You see this here? That duckbill, it ain't opening. Guess what? You send it up to the lineman, and it is not going to be a good situation because he probably is going to holler at you. Well, he's definitely going to holler at you. So always remember, when you send it up to him, send that thing up ready to put on. Do not send it up where you can't get it open. All right, guys. So I guess what I'm getting at is this doesn't in any way qualify you to go out and start grounding lines. It's going to go from the neutral. It always hooks up to the neutral first or the static and then goes on the primary. It never goes the other way around. And another thing, don't get the shotgun and, you know, get up here on this end of it. Don't shorten it. You work at the end of that shotgun down there by the mechanism, because if you're up here and something happens and it goes to ground, it's going to burn your face off, okay? Fellas, if you're on the ground, you don't feel comfortable, whip out them gloves. All it's going to do is make you stronger. And don't be working on it if it ain't grounded, because if it ain't grounded, guess what? It ain't dead. Remember that. Guys, I'm going to get a video. I'll put it in here on how somebody else is grounding it. Till next time, guys, keep that fire in this wire, not in these, okay? And we'll see you right here after the storm on Lyman Universe. Peace.
Peace.
Wow. Pretty good video. Definitely. Where do you think he's from?
Louisiana.
Well, yeah, he's from way down there. You know, guys, you're going to go working in companies and whatnot, and there's going to be different terminology that different companies use for what their pieces of equipment are. I've never, because there is such a thing as a grounding chain, and it's on a cluster mount. I don't call the grounding cable a grounding chain. Have you, Professor V? No, that is a grounding cable.
Right.
It is, let's see. But he does bring up some good points.
In saying that, would the terminology in different states
I mean,
apply to the same thing, but they're just
Yeah.
it's
thing?
Paul, and as part of the industry right there, it's slang. It's lemon slang.
All right.
And
So
you,
when you went up north, I heard you did something on Sandy, right? And you went up north. Was everything different up there as far as how they talked about certain things?
well, not everything was different, but you could pretty much decipher what they were talking about. When we have, you know, the fuse barrel that goes in our switch,
Yeah.
we call that a fuse barrel, and you open the fuse barrel and then you close the fuse barrel. They call it a door.
Yeah.
Up north. Open the door and close the door. Well, it's not a door. To me, it's a fuse barrel. So, you know, it just, and when you say across different states, I mean, I could probably go from Santee Cooper and drive down to Santee Electric or Electric. They're going to have different terminology right here in the county.
Oh, wow.
You just got to, I don't want to say you got to get used to it. You will just get accustomed to what they call things inside your organization. I like to be a little bit more technical. Sometimes you can't get in trouble with what they're saying as far as, you know, what their slang is, because if I was to be given an instruction to go to a fleet and pick up a grounding chain, I would definitely be going to a fleet, and we'll talk. Well, I might show you one. Lineman grounding cluster.
Line main.
Line main, yeah, I know. I don't know if I'll bring it up. Robbie, do you know a better description of the cluster? There it is, right there.
Right in the middle.
There it is.
Yep.
All right. So that, you know, if you were to send me, and I was a new lineman in your organization, and you say, well, go get me a grounding chain, that's what I would go get. Why? It's got the chain on it, and that's the grounding chain that goes around the pole, and that's what you hook your grounding cables to. So, you know, I'll be totally lost in that situation. This, on the other hand, I would call a grounding cable because it's got a cable. I mean, keep it short and simple. So, you know, you're going to run into situations like that. And Robbie's, I mean, I've spoken with Professor Vermelin before, and he said one thing, and I've said, is that this? And he's, you know, that's just from here to Duke Energy.
Right.
So, you know, he does bring up some good things. You just get used to it while you're in your organization by all means. If they say something, well, what the heck is a wire stretcher? Okay, don't get caught on that when there's no such thing.
Yeah.
You know, ask them, well, what do you mean? Show me what that is. And from that point on, you know. Now, he does bring up some good points, though. He does bring out this grounding cable. What color is it?
Yellow.
It's yellow, okay? Yellow cables are used for grounding only, gentlemen. He also brings out, I'm going to go back to this tick tracer, too. He also pulls out a, where's it at? There you go. He also pulls out this red cable. Let me see if I can find out where it's close to it.
Guys,
There you go. That's a mechanical jumper. Now, a mechanical jumper is meant to bypass the flow of electricity. So this cable has got extra insulation on it on the outside and is rated for the amount of amps that are supposed to go through it. So if you have a circuit, say, that is rated for 900 amps, you better use a 900 amp mechanical jumper. And that if you were to give any kind of reference to it, it's like a jumper cable. So I can bypass switches, I can go over cross arms and double dead ends, and I can use this thing to, or I can splice conductors together energized with this. I cannot use the grounding cable. The grounding cable is meant for fault current. So this thing is rated for up to sometimes 10, 20, and 30,000 amps. Two is, you see this duckbill, what he calls the duckbill at the top clamp? It's not insulated. He didn't show you the ends of the mechanical jumper. They are insulated. All right. Professor, if you're going to talk about this tick tracer.
Yeah.
You know, a lot of people say it's not, and he said it too, I like it. It's not dead until it's grounded. That is 100% correct.
Yeah.
But one of the steps a lot of people leave out, and I'm glad he included, is you have to test the line first before you ground it.
Yeah.
And what he's using here is what you call a hot horn or a tick tracer. Now, he said you have to make contact with whatever is energized to make sure that it is not making that tone.
Let's jack it up to 15 kV. Guess what? It's not even recognizing it.
Okay, so it makes that tone. Excuse me. And when you get a solid tone, that lets you know it's energized, but you don't need to make contact. Just get it in proximity of the conductor and it will go solid. Now, here's a warning, gentlemen, and this happened probably about 10 years ago. I seriously doubt they're being made anymore, but they're still out there. There were tick tracers or hot horns out there that made a solid tone all the time, and when you got them close to an energized conductor, went quiet.
Yeah, I like that.
They worked in the exact opposite concept. I did not like those. The guys working did not like those. You had a solid tone when you turned it on. Whenever you got close to an energized conductor, it stopped. I really don't like that. I like the indication of something making a noise when I get close to it.
Yeah.
So test it before you ground it. Anything else that you would like to bring up here, Professor V?
What did you all call your mechanical jumpers, your slang for?
Mechanicals.
We call them Macs.
Well, yeah.
Yeah, Mac it out.
Mac it out. Mechanical jumper.
Yep.
Grounding cable.
Yeah, we just ground. Give me a set of grounds.
Yeah. You see the transformer behind them?
Yeah.
A lot of people call it a pot
Mm-hmm.
because it looks like a big pot. It's just the riser that we say comes out of the top of the switch and the bottom of the switch that goes through the primary and then to the transformer. People call them stingers.
Yep.
It's never ending.
Now the tick tracer you got there, what I like to used to do with mine when I was out on, especially out in the rural areas, I could put it down on a lower setting, kind of hold it in my hand and walk under the primary. And if it was de-energized, it wouldn't do anything, but I could tell if the line was hot and I had trouble somewhere else because it would pick up that magnetic field and go, start to beeping. Yeah,
there are tons of them. And make sure you get one. Don't use one for an electrician, but you see a lot of them right through here. Make sure you get one that's rated for a lineman. That's like this Klein Tools, and it'll tell you the voltage on it. This amp probe, that's a good one.
Yeah.
They are surprisingly, I mean, you look at these prices, $324 and $210. These things are bought like candy and are used a lot.
Yeah.
So be sure that you test.
Yep.
Now, if you're testing, just like he said before, if you're testing secondary voltage, just use a pair of rubber gloves, hold it. If you're going to primary voltage, put on a stick.
Yeah.
They did have at one time, and we kind of got away with it, looked like a little pager that you wore on yourself. And actually that started beeping every time you got close to an energized conductor, anytime, if you were walking around, if you were doing anything. I mean, they worked cool. They were kind of nice, but we worked energized conductor almost all the time. So the thing was just going off all the time. Yeah. It was kind of.
They, when our engineers go off on storms with us, they go out and bird dog or whatever, But they have a similar device that they wear around their neck, and if they getting close to energized conductor, to go off and let them know, hey, that's an energized conductor on the ground or hanging low or whatever, for them to back off.
Yeah, you don't need to activate it. It just stays active all the time. So if you come close to a conductor, it will go off.
Yeah.
All right, any questions on the video? Good one.
Yeah.
I enjoyed it. I liked it. Had some good information in it. Big points here. Test it out before you ground it, and ground it before you work on it. Those are the big things. Okay. All right, so let's go. Time holding here, 9:29. Let's go run into the book here. I have moved up to Unit 12, page 300, three-phase circuits. So if you've got a book, be sure to make some marks in it, because there's going to be a lot of stuff in here we're going to be talking about, or take notes. So start off the first paragraph. Most of the electrical power generated in the world today is three-phase. Three-phase power was first conceived by Nikola Tesla in the early days of electric power generation. Tesla not only led the battle concerning whether the nation should be powered with low voltage direct current or high voltage alternating current, but he also proved that three-phase power was the most efficient way that electricity could be produced, transmitted, and consumed. And there, we're going to go into the specifics of why here on the other page. Let me catch that real quick. One dropped and I got a text. Oh, we lost Professor Vermelin. He's having some severe internet problems down there. All right, three-phase circuits. There are several reasons why three-phase power is superior to single-phase power. One, now this is going to be a test question. The horsepower rating of three-phase motors and the kVA, kilovolt amp rating of three-phase transformers is about 150% greater than for single-phase motors or transformers with a similar frame size.
Can I get the page number again?
I was 300. I'm at the top of 301. So really, in a roundabout way here, and not saying it more in practical terms, is that I'm getting about 50% more efficiency in both the output of the transformer and in my motor when I use three-phase. It's 50% better because I'm using three-phase power, and we'll get to the reason here in just a moment. Two, the power delivered by a single-phase system pulsates, and you'll see that on the right-hand side of figure 12-1. The power falls to zero 3 times during each cycle. The power delivered in a three-phase circuit pulsates also, but it never falls to zero. In a three-phase system, the power delivered to the load is the same at any instant. This produces superior operating characteristics for three-phase motors. Okay, I'm going to bring up a little diagram right here. This is vitally important in three-phase systems. So here I am in generation, and this is now a three-phase generator with three-phase output. What they're saying in the book there at number 2 is, if you look at the diagram on the right-hand side where it shows the 3 waveforms, any time, and time is on the bottom, through this sine wave and my voltage current output, the voltage is the same all the time. Now, it might be different between each one of the phases, but the combination of all 3 phases at one point in time is always the same. Is that understood?
Yes.
Okay. That's why when we say in a single phase system, I'll use the blue line for single phase. If that is 7,200 volts I'm generating, 3 times in this sine wave, it's at 0. If I'm using all 3 phases at one time, all the time I have 12,470 volts all the time. So you can see how that efficiency is much better in a three-phase system. Any questions there? Where did I get 12,470 from?
You multiplied it by the magic number 1.7325.
Right. I took the phase to ground voltage here of one phase and multiplied it by 1.7325 to get my three-phase. Now that's a combination of A and B, or B and C, or A and C. Any combination of any two.
Question real quick.
Or the combination of all three.
Message Jimmy.
Yes, sir.
If three phase is the most efficient phase to use, why would you use a single phase?
It depends on the load that you're trying to feed.
Okay.
Okay. As far, and I'll go back a little bit of this in the past. In the 1960s and 70s, people started getting three-phase motors for their air conditioning units in homes. And actually, the utilities started supplying three-phase electricity to those customers for the AC units in their homes, and it was more efficient. When you're able to produce voltage all the time, that means also that you're able to supply a demand load of amperage, and your bill's going to go down. It's just more efficient in that process. So it's a plus both for the utility and for the customer. Well, motor construction became much more efficient in air conditioners, and it was deemed okay we're just going to go down to a single phase motor in an AC unit, and that motor load inside a home is now, I would say, negligible. It's low enough that single phase is able to power it sufficiently.
Okay.
In retrospect, there is so much, and we use the college again for example. In retrospect, you look at the college and it's just full of motors. Every building is going to have an air conditioning motor with multiple units. They're pumping their own water and ammonia for chillers out there at the college. So there's just a lot of motor load out there. Three-phase is going to be more efficient in that situation. Is everybody familiar with CAM4? Or know what CAM4 is?
Yeah, so
Yeah, it's a lumber yard. And what do you think they run out there as far as what kind of load that they have?
they probably have three phase too. Bricks would know.
It's almost 90% three-phase. The only single phases they're running is lights. The rest of it is saw motors. So that gives you a good example of the extreme on one side and the non-extreme on the other. Okay, any questions there? That was number two, a more descript definition of number two on the page of 301. 3, in a balanced three-phase system, the conductors need be only about 75% of the size of the conductors for a single-phase two-wire system. When they say two-wire, that's a primary and a neutral of the same kVA rating. This helps offset the cost of supplying the third conductor required in three-phase systems. So, and it goes back to the basics that we're learning right here. If I'm using a three-phase system and I have a constant voltage all the time, I'm going to have, how many phases do I have in my drawing right here, my motor that's running? How many energized phases?
3.
3. How many neutrals do I have?
1.
1, and that's the center one right here. The center one is grounded. So I have 4 wires. If I'm able to distribute electricity on 3 phases at a constant voltage all the time, I'm able to actually reduce the size of those conductors because I have constant voltage. Make sense?
Yeah.
Yeah, so my voltage size can actually go down. This is vitally important when I start working on transmission lines. If I have constant voltage all the time on 3 phases, I'm actually able to reduce my conductor size even more. One process is I'm stepping up the voltage so I can transmit it. The other one is I'm using three-phase, so my conductor can be even smaller and more efficient. It's called load sharing and load, like they say in the book, load balancing. Okay, any questions there?
So you can reduce the size of the conductor because it's constant.
Because your voltage is constant between all three phases.
Okay.
And think of this. If I had just one phase of transmission and I needed to supply 900 amps on that three-phase right here, and this is going to be a pretty decent description, three times every wave, I need to remake that 900 amps from zero. It's called what they call it out there in the world, shock load. Really, is I have to make the load. All right, I'm giving the voltage that's most efficient for it, so my load's going to go down here at the top. I'll come down to the bottom. I have to remake the load. When I say, you know, re-energize the load, now I'm here at the top. Now I'm being the most efficient. In three-phase, all three phases are compensating for the load that's being supplied.
Yeah, they offset the other one.
So on that shock load that's coming up here at the top right here, I need to make my conductor size bigger to be able to compensate me making it up all the time, making it up, making it up. When I have constant voltage, I'm able to reduce that size and get a smaller conductor. Another property of this right here, and we'll talk about this when we get into different three-phase systems, they talk in the book here in a balanced three-phase system. This is also vitally important because there are different techniques that are used in generation and distribution, transmission and distribution of building three-phase systems. Whereas if I have 900 amps, let's go back on this one. If I have 500 amps on this phase, 450 amps on the green phase, and 550 amps on the red phase, what the three-phase generator will try to do in this process and transformer is balance those phases on its own. So it'll say, well, this one's a little bit high. I'm going to try to load balance with the other two phases to kind of even it out. And that, once again, is going to reduce your conductor size. Load balancing. We'll talk more about that a little bit later. But that is, you know, those are the essentials right there to know of why we have a three-phase system. Just as a disclaimer here, and we'll talk later about this too. In a generating station, do you think in the generator I just have a huge magnet that's turning?
No.
No. What am I going to use inside here? This is static. These are the static coils that are on the outside of the generator. These are coils. What do I have on the inside?
Movement.
Well, movement of what?
A magnet.
There is no magnet in the middle of a generating station generator. What am I using instead?
Metal rod.
What do I need to create in here? This is a good question for all you guys. What do I need to create in here to go across these coils?
Magnetic field.
A magnetic field. And what can I create a magnetic field with?
Wrapped copper around a steel core.
There you go. Yeah,
With electricity on it.
what I'm going to do is I'm going to make two sets of coils in here, wrap them, and I'm going to have to energize them. It's what they call an exciter current. You actually need electricity to make electricity. Once I get the exciter current inside that set of coils and I start spinning it, it's going to be self-sufficient. But I'm not going to be using a huge magnet. One, is too frail. And two, it's not just, there's no such thing as a magnet of that size. So you're going to use another set of coils that you're going to have to do what they call put an exciter current to it. And it makes its own magnetic field. Once that magnetic field is created, it just starts feeding off each other in the turn. Another thing about this illustration right here, it's kind of fast, but you'll notice how many coils do I have for A, B, and C each?
2 for each.
2 for each, right? You'll notice when the north goes around one side, it peaks, and when the south comes around, it does what?
Peaks also.
Peaks about at the bottom, peaks at the top, peaks at the bottom, peaks at the top, peaks at the bottom. This, gentleman, is AC. It goes up, out, comes back, out, comes back. That's how AC is done. And then you have the other, two sets of coils, B and B and C and C. That are the other two phases that are introduced. Okay. All right, it's 9:45. Let's take about 10, and we'll come back at 9:55. So we'll get started back here. So we had spoken about the three-phase generator and how three-phase works, its properties. And in turn, I'm going to go ahead and show you here the product that uses it. So prior to that, I had shown you the three-phase generator in this process of how we're getting output. And, in a generating station, manufacturing, generating property, we don't use a magnet here in the middle. We're going to use a coil that's producing its own magnetic field. The end product here is, well, what are we going to use it when we get it to where we need it to go? And I've got up here what they call an induction motor. Now, I'm glad the way they put this here. When we're using three-phase and we've got a motor, what kind of load is it? We spoke about this yesterday.
Induction motor.
Yeah, it's an inductive. So there's, for a motor to work and a motor to turn, obviously, sir? I thought you had said something there. Obviously, I can't have anything making contact here for the rotation of my motor. It's got to be free to be able to turn. So I've got to induce voltage from coils onto another set of coils in the motor to be able to make it to turn. Now, in single phase, what makes a motor turn? One single phase. And we'll use A here for an example. It goes from peak to peak in two different directions. So back and forth, back and forth, back and forth. And that makes the rotation in a motor for single phase. I'm going one way and the other, one way and the other. So north, south, and that will eventually get a motor to turn. Not the most efficient in a motor because, like we said before, every sine wave that we have of one single phase, it falls to zero. So it's going to take a lot more energy to get it, one, started, and two, it's going to take more energy to keep it running because 3 times every sine wave, I'm falling to zero, I'm losing my voltage. In three-phase, I have 3 different phases that are able to power the motor all at the same time. And actually, in rotation, I'm able to push with A, and then B, and then C. A, B, and C, A, B, and C. And, I'm kind of saying in a slow motion. When this happens right here, this is happening how many times per second?
60.
60 times per second, I'm using 3 phases of power to be able to turn a motor. So you can see the efficiency has become much greater in this situation. I kind of like to wish in this diagram that the arrows were pointing in rather than out to let you know power is being introduced, being introduced into the motor at all these times. Now there's something here I also want you to look at. In my diagram here, what is the phase order? What's the phase order? A?
Blue, red, green.
Blue.
Blue, red, green. A, B, C.
Hold on a second.
It's showing blue, green, red.
It's showing blue, green, red. Okay? And you can have different phase rotations anywhere out there in the world. We'll talk just about this in a moment. As long as the generator and whatever you're powering matches. So in my generator here, I have phase A, phase C, phase B. What is my rotation, clockwise or counterclockwise?
Clockwise.
Clockwise. So that's the way my generator is rotating. If I match my motor in the same phase order, A, C, B, what rotation will I have in my motor?
Clockwise.
Clockwise. I can guarantee you, gentlemen, at the generating station, this is never going to change. All generators go in a clockwise motion. All right. If I have a motor that I need to wire in a different phase rotation, all I have to do is swap any one of the two phases. So if an electrician has gone through a building and in the wiring process somehow has crossed A, B, or C going to the motor, all we have to do is, as far as the utility is concerned, and this is just for one motor, swap and put C in the place of A and go CAB or BAC. So phase rotation can be changed by the swap of any one phase with another. Once I have done that, my generation stays the same. It's always going to stay the same. Once I have done that, this thing will now turn in reverse. This is a good thing to know out there in the world, just in case you're wiring something up. Now you might go and Professor V, you can chime in on this too, as far as what you've seen out there when you're working with three-phase or whatnot. Typically, out in the utility, we, as far as us building it, are going to try to build it in a concept of what? To keep things straight in our minds. A, B, C. Left to right. A, B, C. I can pretty much guarantee you the generating station, also in its concept, is going to put out conductors that are going to go A, B, and C. But I'll let you know what happens out here in the world. Professor V, you agreement on that?
Absolutely.
Okay.
Yeah.
Uh,
We've gone to many jobs before where we've had to upgrade facilities or just install new facilities, and we get our stuff in there, and the customer himself or his electrician will have to make sure they have the correct rotation for their motors.
there you go. Excellent.
Yep.
Now here, I'll use this for example on a photograph right here, and bring this one up in the screen. Through our entire distribution and transmission system, things might get rolled or rotated. Now in transmission, our optimum would be, if I was to look at these post insulators here, top A, middle B, bottom C on both sides. That's double circuit transmission. You see how these conductors roll? Here they're vertical. Now they're horizontal. So A is on the facing the pole. We're behind it, facing the pole. A, B, and C. And then it transitions to what? Underground conductor. There's going to be multiple times that you're going to go through an electrical system where looking at the conductor itself is not going to be in the A, B, or C configuration left to right. That's one thing to remember out there in the world. You're going to attempt to build it in that configuration, but it might not always be in that configuration when you initially come to it. There are so many different turns and junctions and rolls. This is a roll right here. I'm going from vertical to horizontal in a system, that it might not be the A, B, C configuration. That's where you have to jump back to what Professor Vermeulen just said. You have to post-check it before you send it to the customer that you're in the right rotation. Okay. Big thing to remember there in configuration, left to right, A, B, C. We also go on a color method. Who are my electricians here?
Yep.
Yeah, when you do three-phase wiring, what is the color coding that you use for three-phase?
Brown, orange, yellow.
BOY. Now they call it the boy. Brown A, O, B, Y, C. In electric utilities, it's another color configuration, and there's a reason for it. It's to be able to discriminate what's the utility and what's electrician. The utility is going to use red, white, and blue. the good old American flag. Red A, white B, blue C. So if you needed to match your configuration of utility to customer in a wiring process, red would go to what for the electrician?
Brown.
Right? White would go to what?
Orange.
And C would go to what? Blue.
Yellow.
Yellow. There you go. Great configuration. All right. I'm on the page 302.
Can
Okay.
you repeat that red, white, blue? Which one?
Red. All right, here's the configuration for the utility. Red A, white B, blue C. All right, in an electrician's configuration, B, brown, A. O, orange, B. Y, yellow, C. Good to go there?
Yes, sir. Thank you.
All right, you're welcome. All right, once again, and this is just another good figure here on page 302, figure 12-4. And do remember this as far as concerned, I'm going to ask a couple questions on it on the test. The voltages of a three-phase system are 120 degrees out of phase with each other. Paul, this actually goes back to the calculation, or how we're able to do the calculation. How many degrees, and I'm going to just go use the A phase that's on the top there, just the one single phase. How many degrees are there in one full rotation of one phase? One full rotation.
360.
360, okay? So once I add the two other phases, and now I have three phase, they're just bouncing back and they're going the opposite direction. All right, one full rotation means that each phase is 120 degrees out of phase with each other.
Question.
Yes, sir?
Why did they stop at 3 phases and not go to 4 to make it even more efficient?
You know what, Paul? Professor V, you probably attest, every class has asked that, haven't they?
Yep.
Every class has asked that. So stand by. There's a professor that actually did a study on this.
You want me to post it? I got it up.
You already got it ready?
Yes, why 3-phase power, not 6 or 12?
Yeah, I'll stop my share. You can share it.
Coming up. Pause.
First day of class.
Coming up. Let me know when you see it.
Hey, Shoemaker, can you see me? My computer died and I'm on my phone now.
Who are you?
Caleb Cook.
Hold on, Caleb Cook. Oop, I think I went past you.
It says it has me in safe driving mode and that my camera is disabled.
Why are you driving?
I'm not driving. I'm sitting in my room.
No, we don't see you.
No.
Said you don't see me?
Uh-uh.
All right, Professor V.
Ready?
Yes, sir. Go ahead with it.
Possibilities and unknowns. That's why Check Study Pack empowers.
You see it okay?
Yeah.
People chose 3 phases when they transmit power. Why not 4? Why not 5? Why not 12? And I realized that if you took a 3-phase transmission line and then you took a second one alongside of it and you rotated this one 60 degrees electrically, you could put it inside of the first one. And the circle isn't getting any bigger. But now you have, it would seem, twice the amount of power. You would, in fact, have almost twice the amount of power. Now you have a 6-phase line instead of a 3-phase line, but the voltage per foot between phases is the same because you reduced the voltage between phases by changing
Can you
rotating.
pause it, Professor V?
I can pause it right there.
So what he's talking about there is, you know, when he, I don't want this to go over your heads too quick. When he says that you have twice more power, you're not raising your voltage and you're not raising your amperage. You have more availability at a point in time. Does that make sense?
Mm-hmm.
Yeah. Your voltage is at your peak. It's at your highest peak in time more than it is in 3 or single phase. And that's really going on the concept of all when you start introducing phases. So that's why I'm saying he's not raising his voltage. He's not lowering his amperage. He's got power, and I kind of like the way he says it. He's got power availability in time more. Go ahead.
If that works for 6, why can't you put another 6-phase line inside of a 6-phase line, rotate it a little more? Now I have 12 phases. If that works, why can't you do it again and again and again until you have a tube that is a conductor longitudinally, a funny material, but it's an insulator circumferentially. It's an anisotropic tube. And if you want an interesting adventure in mathematics, figure out the characteristics of that tube. It's doable. But in a more practical vein, during PTI days, we proposed some serious look at the 6-phase and 12-phase line. It turns out that the gain in power is not proportionate. 6-phase almost doubles 3-phase. 12-phase does not almost double 6-phase, so it's a diminishing return.
Could you pause it there?
Built.
All right. Do y'all understand what he's saying right there? The power availability is there, but the difference between 6 and 12 phase is just negligible. You've got your sine waves so close together there. The power availability in 6 phase and the difference between 12 phase is just so small because you're peaking almost all the time with 6 phase. It's just not worth it. Go ahead, Mr. V.
PTI had a test site in Malta, and we actually built, I made a model of it at the time, I still have it, of how a 6-phase tower might look with these blue lines are the insulators. Here's another one with a center conductor. We built such a line, I tested it. It worked exactly as you would predict it, so the math proved itself. Nobody was surprised. And, you know, one got a little excited about it until you realize that a 3-phase line, when it goes into the substation, has 3 circuit breakers to open it, close it. And throughout that substation, there are 3 bus bars that these connect to. With a 6-phase line, there would be 6 circuit breakers and 6 bus bars.
Okay, go ahead, pause it. So there it goes. We're getting down really to economics here.
Mm-hmm.
All right, so 3-phase and its efficiency is good. If you went to 6-phase, I'd pretty much have to double every single conductor, every single piece of equipment on my system. So you'd have to have double the cost of everything that you're going to construct on your utility system once you went from 3 to 6-phase. Go ahead.
phases, there would be 12 circuit breakers and 12 bus bars. So the complexity of coupling it's called a high phase order line, of coupling that into a substation sort of defeats the economics of it. Although periodically people raise the question, because it would be possible, for example, it's very easy to couple from 12 phases through a transformer down to 3 phases. But it remains an intriguing concept, probably more useful for power educators than for transmission line companies.
Engineering pioneer.
I mean, I've seen some videos by him before. He's smart. That's all. Yeah, that's pretty much all I could put it. He's you know, and I like those short videos. I mean, you're going to get some engineers that go out there that, wow, I mean, can really talk you off the edge of the planet. But that question has come up in every class of why we don't use 6-phase or even beyond 6-phase. And he gives a good short description of why. It all turns out to economics. And, you know, the kind of nice thing is he tested it.
Yeah.
Okay. All right, back to our books here. I'm at the page, bottom of page 302. As far as 3-phase configuration.
What page again?
302. Okay, as far as connections, now there are two different connections types in the in your electrical scheme for utility, and both the electricians. There are two different types that we're going to be using. One is called the Y connection. Now the Y or star connection is made by connecting one end of each of the 3-phase windings together as shown in figure 12-5. The voltage measured across a single winding or phase is known as phase voltage. If you want to put a marking in your book right there, that is phase to ground voltage. The voltage measured between the lines is known as the line to line voltage. We call it phase to phase voltage, and it's called the line voltage. So let me get a drawing right here and try to simplify this wiring diagram for you. So let me go to let's not do that yet. X that. Paint. All right, and let's go to a share screen.
Are we going to learn about line and load?
Okay, there's a lot of echo and R2D2 there. Say that question again.
Are we going to learn about line and load?
Winding load?
Line side and load side.
Line side and load side?
Yeah.
Referring to what? Never heard of that before.
Like the line side is coming from the power source. The load side goes from the motor.
Yeah, we just talked about it a couple moments ago. We learned a little bit about it. Do you remember?
Yeah, I didn't know if we were going into detail.
We will be. I mean, we're not going to dwell much on the electrician side. We're going to stay on the utility side. But we'll be talking about it some more. Okay, do you see that share screen of paint?
Yep.
So you're looking at the diagram at the bottom of page 302. That diagram is of a Y connection. So I will draw one also. Let me get my pen right. Make sure that when you draw a Y connection out there in the world, you include the squiggly line. What they do not include in this diagram, and is typically in some diagrams here, is, and it helps me out a good bit, is this symbol right here. And what is that?
Conductor.
Ground.
Ground.
Oh, ground.
Right? And this really helps in what they're explaining here in that bottom paragraph. The voltage measured across a single winding or phase is known as phase voltage. So what they're saying here is they're taking a measurement from here to here, and from here to here, and from here to here. That's what they're saying in that line sentence right there. So we're going to go ahead and apply some voltages here. There's 7,200 volts on this phase, 7,200 volts on this phase, and 7,200 volts on this phase. What is the phase to ground voltage? I just wrote it for you.
7,200.
7,200. That's the measurement from this point to that point. Going on in the paragraph. Now they call it line voltage. That's kind of not descriptive enough for me. That's shown a figure. The voltage measured between the lines is known as the line-to-line voltage. I like to call it the phase-to-phase voltage. So that measurement is this point to that point.
12,470.
There you go. This point to that point, or this point to that point. And I believe Mr. Echo Man has already given us 12,470. Good job. Took 7,200 and he multiplied it by 1.7325. Excellent. That is the Y configuration. A good thing to remember here also is when we start working with transformers and transformer banking in three-phase, that this is one transformer winding, this is two transformer windings, and this is three transformer windings. That is three separate transformer windings. Now I can have them encased all in one case, but that is one winding apiece for each primary phase. Another helper right here would be to A, B, and C is to go ahead and letter your different phases. So if I was to look at an actual power line, top phase on the pole, phase on a cross arm, phase on a cross arm. This is the special thing to look out for here on a system. What am I using here? A grounded neutral here at the bottom. And this is how you can distinguish just by looking at a power line if it's a Y configuration or a delta configuration. How many phases do I have?
Three.
Do I have a neutral?
Yes.
Is it grounded?
Yes.
That's a Y configuration. All right, over on the page, bottom of page 303. I know I gave this to you real early in math. We're finally going to get to it in the book. Second paragraph, in a Y-connected system, the line voltage is higher than the phase voltage by a factor of the square root of 3, which is 1.732. I add the 5 because that is correct, and it gives you just a little bit more precision. So whenever I take the line voltage and multiply it by 1.7325, you then get the phase-to-phase voltage. Any questions there? Remember that. One thing to do, and we're going to be getting into this pretty heavily, this applies to any phase-to-phase voltage when I change primary phases. or I have additional primary phases. Let me erase this. Before, these were primary windings in my transformer. And remember, I've got to have two sets of windings in a transformer. So I'm going to have a set of primary windings. Excuse me. A, dang it. A, B, and C. What must I also have in my transformer to produce secondary? Do I have to have another set of secondary windings?
Yep.
Yes.
Okay, remember in my transformer, I'm doing this number right here. Seen that drawing multiple times? Primary winding, secondary winding. That was back in math when we were doing ratios right there. In order for me to do transformation from primary to secondary, this is Y. Y. I've also got to have the secondary windings over here. We're just going to give different voltages. If my phase to ground voltage on my primary side is 7,200 volts, what is my line to line voltage? You've already answered that. Somebody already answered that before. $12,470 volts, right? In transformation, if my output voltage is 120, 120, 120, what is my phase to phase voltage on the secondary side? I'll wait on this one. If you're having difficulties, look at figure 1210.
207.9.
You're right, round it.
208.
208 volts. So this applies to any time that you have three-phase power, both in primary and secondary transformation. Once we have introduced a different primary phase, our secondary is also going to be affected by the addition of the extra phase. You bounce all this back to try to get the relation of why are we getting 12,470 and why we're getting 208. It all comes back to I'm not getting full power out of all three phases at the same time. I'm only getting 1.7325. The thing to remember here is it happens on the primary side and secondary side of the transformer. That effect goes through the entire process. If you really were to think about it, file, new, don't save. When I use three-phase, from generation all the way to the meter, my phase to phase on all conductors, 1, 2, 3, I'm going to include a neutral, 4, my phase to phase is always the phase to ground voltage times 1.7325. That's in three phase, regardless of where I'm measuring it at. What time are we holding there, Professor V?
10:30.
Okay. We'll go into delta, then we'll wrap. In fact, we'll do two more things here. We'll go into the transformer at the bottom of page 304, and then we'll go into delta, its configuration. And then we'll wrap it up. Okay, I'm on page 304 at the bottom of the page. I'm sure I'm kind of wondering why Paul hasn't asked this or somebody else, because I know the way their minds work. Look at the transform at the bottom of page 12 dash, excuse me, not page 304, figure 12-8. I'll draw it out in configuration right here. Okay, that's my primary. I'll go ahead and put a voltage to it, 7,200 volts. This is going to be grounded. I'm going to do my secondary windings. 1, 2, 3, 4. Come here, here, 1, 2, 3, 4, whatever. All right. Now, if you were to picture this out here in the world, that's the primary bushing on one side of the top of the transformer, and that's the primary bushing on the other side of the top of the transformer. Here are the secondary lugs on the transformer. All right. If you notice the voltage reading, if everybody's got their book, what kind of voltage reading am I getting out of this transformer total on the secondary side?
480.
On the bottom of page 304?
Oh, 240.
240, okay?
Add it
I've
up.
got 120. This goes to neutral and grounded. I've got 120 from these 2 points. I've got 120 from these 2 points, but the combined of these two is 240. Well, Professor Shoemaker, we just got finished talking about Y. And 2 different phases of secondary, I told you, equals what? 208, right? How am I getting 240 volts out of this transformer? Think of the AC waveform and direction.
Because it's going back and forth.
Right. My primary coil is going this way, then it's going that way. I am wound. Now, this is the important part. I am wound in this direction. Windings are going in that direction. What about the secondary side? It's got to do with the winding direction.
Does it go the other way?
You're close. You're close. Think of this is one winding. This is one winding. That's the second winding.
They're winding towards each other.
So you're saying that I've got a winding going this direction and this direction.
Yeah.
Either way, one winding is opposed in the other.
Right.
Okay. Control. See. All right. I can take on my transformer and I can put one winding in this direction and one winding in this direction. What is happening here? Now it's not to the millisecond of every second. Is when I have this going this direction in the AC waveform, and remember that is what, 1/180th of a second. I've got my full magnetic field is being captured by this winding. As soon as I go back the other direction, the full magnetic field is caught by this winding. Each one of them produces 120 volts. And in time, when I combine the two, I get 240 volts. That's how a single phase transformer is able to produce 240 volts. To simplify this, primary windings equals one direction and not the pop group. Secondary windings equals two opposing directions. So I'm able to capture both this peak and this valley with two separate secondary coils.
Is that because of magnetism in north and south?
You got it.
North versus north and south versus south, right?
You got it. Absolutely. That is the concept of how I'm able to get 240 volts out of a single phase transformer.
Does that explain when you have magnets and you have to be a certain way to connect to one another?
Right.
Each
Right.
other?
Right.
All right.
Right. Once I have got two different magnetic receptors on the secondary side that are going two different directions, one's catching north, one's catching south, one's catching north, one's catching south.
Right.
All right. Remember, this is going north and south all the time on the primary winding here on the top.
Yeah.
So at that point in time, I'm able to produce 120 and 120, not at the exact same time, but close enough to produce 240. It's just like I told you. I mean, really, in essence, right here, how many times per second am I at zero?
3.
180 per
right.
second per second. So this is fast enough and capture enough. This is where you get 240 volts. Okay. That's going to be a test question. How am I able to get 240 volts out of a single phase transformer? When I say single phase, one primary phase. Primary windings in one direction, secondary windings are in two opposing directions. One's going this way, one's going that way. Okay. Bottom of page 305, and we'll wrap here. Yep, 1037. Delta connections. Figure 12-13. That's going to be on the next page. We'll show you in just a moment. Figure 12-13, 3 separate inductive loads have been connected to form a delta connection. So let's go ahead. I'll draw it out here for you. New. Don't save. And it looks just like the ones that you see in the college, alpha, delta, sigma, pi, whatever that is. That's kind of nasty right there, but it'll work. So that's what they're using for a delta connection. Now, there's some things that are going on here that are a little bit different from the Y. Y, we had what was the center one? What was the center connection right here?
Ground.
Neutral and ground, okay. Where's it at in the delta?
Bottom. Looks
Not-
like, looks like the bottom right. It could just be
actually, that's just a bad piece of my drawing right there. Okay. I'll fix that. Okay. So does anybody see a ground connection in a delta?
No, sir.
No, there is none. No ground connection in delta.
Why is that?
We'll tell you here in just a moment. Okay. One of the things, how this property works in delta is, delta works on the difference of potential between each phase. So when this phase in my generation is at full 7,200 volts, where I've got the arrow to, is this phase at full 7,200? No, yeah. No. Remember in generation, I'm doing like this. This, that, and this. Nothing's ever the same as far as my wave. It's the phase voltage times 1.7325. So there's a difference in potential between all three phases. And that, we know that a difference in potential is, when we talked about step potential is, that's voltage. So that's the concept of how this works in delta. There's a difference in potential between all three phases at one time. It's kind of squirrely to even think about. Here's a phase to ground. Here's a difference in potential with three phase. And that's really, you're going to have 7,200 if you were to take a measurement to ground of each phase singularly, you're going to get the phase to ground voltage. But in delta, it's working on the concept of 12,470 all the time if I'm using a generation of 7,200 volts phase to ground. Difference in potential between all three coils. And you'll notice in the Y, I'm going phase to ground, phase to ground, phase to ground. In delta, where am I going? Phase to phase to phase to phase. That's why I'm getting 12,470 all the time as the output on it. Now, why do we use delta? There is a humongous use of it for one part of our utility system, and that's in transmission. As far as distribution is concerned, Professor V can attest to this, delta in distribution is going away.
Mm-hmm.
There's just not as much delta as there was on a distribution system, and the huge reason is this right here. I don't have a neutral or ground. Either I've got to have the customer supply one, or I've got to produce one to be able to have another safety feature going on here.
Yep.
Why do we use it in transmission? Well, let's bring up a transmission picture right here. Share screen, screen one. Share. All right. You should be looking at my Google screen. Is that right?
Yep.
Okay. Transmission lines. We'll get some images going on here. Okay, let's try to get a more simplistic one. Not double circuit, if I can find one. How do we use this one?
They have the old pyramid ones in the UK.
Yeah. I mean, they've got structures that are made out of deer that look like deer and animals and whatnot. You can get pretty creative with it. All right, so the image that I'm throwing up on screen here, I've got one, two, three phases of transmission. Where's the neutral? This is delta.
Is that it up top?
Nope, that's a shield wire for lightning.
It doesn't have
Right
one.
hand side running off.
Who just said it doesn't have one?
I didn't.
Somebody did. Okay. Somebody just said it doesn't have one. And whoever did say that, you're absolutely correct. There is no neutral.
I said it.
Now he claims it.
I thought I was going to get yelled at.
Well, I'm going to yell at you. Good job. Yeah, there's no neutral on this, and transmission does not use a neutral. It's not required. As far as its voltage is concerned, it's going to be a phase-to-phase voltage for the entire transport down to the substation. Now, the reason why it doesn't need a neutral, it doesn't use a neutral, is, I mean, for one, it's just not required. When it gets to the substation and goes beyond the substation, that's where conversion takes place. Utility substation. Okay. We'll go ahead. Well, yeah, we'll use this one again. 34 kV is a what they call sub-transmission. Why did that picture not show up? Open image in new tab. So I've got my 34 kV substation. Now over here on the side, this is double circuit 34 kV, but there's still no neutral on this 34 kV system. The shield wire is here at the top. So they're coming in with 3 conductors delta into a protective breaker, going over to the transformer, and guess what's happening at the transformer? Before I showed you an image on my screen, and that image of transformation was Y Y. I had Y input, then I had on my primary side, and I had Y output on my secondary side. What is this? What is the transformer doing in this substation? In delta, out Y. There you go. It's happening at transformation at the substation. My wiring configuration in the transformer is input delta, output Y. Once I go output Y from this point out and out to my distribution system at 7,200 volts, I now include a neutral. So configuration wise, as far as drawing is concerned, that just goes back to show you, I don't need ground or neutral, excuse me, you do need ground. I don't need neutral on my transmission system, because where is it going to? A substation. And from that point on, do I now need a neutral out of the substation? That's where you're going to need it at. Also, and we're going to talk economics again, if I don't need a neutral on transmission, I don't need to pull one. That's an extra conductor I don't need. Okay? All right. Wow, Professor V, am I burying them?
Yeah.
Okay.
Smoke rolling out.
Smoke is rolling out. Just as another share here, I'm going to stop this share and go back to the paint screen. In a drawing configuration, new, don't save. My substation transformer is in a configuration like this. Primary windings, delta. Secondary windings, Y. Oops. This will actually be on the nameplate of the transformer. Yep. Some transformers, some three-phase transformers that you're actually going to be installing have the configuration on it for you. So my transmission input, delta, my distribution output, Y. I think I've buried them enough today.
Yeah.
That's a lot of information for one morning. Any questions to this point?
At any point, would you ever go from substation to substation?
Yes.
Would you need to do that configuration change if that's the case?
No. This is going to be your normal substation when you go from substation transmission to utility distribution. That's going to be your normal configuration right there. They do there, and not to say, there are some systems out there still that are delta for distribution, but they are fading away very, very quickly. Okay? It's going to delta Y because now I'm in your delta Y configuration. I'm introducing a neutral and a ground, and that's just more safer. There are, though, in transmission, and you're going to stay in the transmission scheme, generating station down there in Winyaw, its output voltage is actually 230 kV. And it's going out to, and I'm not going to show you on a map, it's coming up to 501, and right off of 501, there's a road called Perry Road. And there's a Perry Road substation. The input voltage is 230. The output voltage on 4 separate circuits is 115 kV. So I'm going from Georgetown to Conway, and from Conway transmission, I'm going to Conway. I'm going down to Garden City, Myrtle Beach. I'm going up to North Myrtle Beach, the state line. And all my substations are then fed off of 115 kV. Now, there are some other stations between here, Georgetown, Winyaw, and Conway Perry Road. There's a couple more down in here. There are also 230 going to 115 kV, but this is the one to focus on right here. Why did I transmit at 230 all the way from Winyaw? Y'all know this already.
The long distance.
Go a longer distance, smaller conductor. And that's a long distance. We're talking 35, 40 miles down to there. Now that I'm going to 115 kV, I just don't have to go that far to reach the North Carolina state line. It's 10 to 15 miles, 20 at the max. Your configuration, Paul, in this substation is still delta, delta. That transformer that's sitting in that substation that's converting 230 kV down to 115 kV is still delta delta. Is that the question you're asking?
Yeah, so they just split it. They're just distributing it. My question really was, you know, if you're going from substation to substation, there's still no need for that neutral line.
You are correct. Yeah, you are correct. You know, and actually, when you take a look at the transmission lines that are out there in our field, what's going on out there, that's 115 kV. I'm sure you kind of recognized it. Right up there at the end of our field, closer to Myrtle Beach, there's 3 lines, and they're, I mean, relatively low, going down that right of way to the substation. Here's 501. Here's our field. Okay, and there's the substation over here. Is there any neutral with it? No, no neutral. So I know that's delta. That's after it's been transformed at Perry Road. That's that 230 to 115 kV station. Now, once it gets to the station, down here at the end, my substation, and I'm going from transmission to distribution, that's going to be delta Y in transformation. The lines that are coming out underground are 3 phases, 1, 2, 3 phases, and a neutral. A, B, C. And those go down all over the place. Does that do it for you?
Yeah.
Okay. All right, gentlemen, if there's no more questions, Professor V and I through lunchtime here are going to create a quiz. I will post the video from yesterday. This video will be processing and will be uploaded also. The quiz will be announced to you via Remind, and you'll have until midnight tonight to complete it. Also, after lunch, if you got questions on the quiz, if you start working on it, we will be in the Zoom room at 12:30. If you have questions on your presentation, those can also be addressed in the Zoom room after 12:30. We'll be turning it off at what, 4 o'clock?
Yep.
4 o'clock this evening. Okay, with that.
Presentation is due Monday morning or Sunday evening?
Monday morning.
Okay.
Monday morning, 8 a.m.
8 a.m.?
Sorry about that, 9 a.m.
9 a.m.
Okay?
All right.
All right, if there's no further questions, we'll go ahead and take a lunch break here, and Professor V and I will be back online at 12:30.
Sir, I do have something a bit personal. It's not about what we're learning, but
I'll stand by 1 second then so I can stop recording.